While studying functions f from R to R, there was one technique that came quite handy to check whether a given function is continuous or not. This was called the sequential criterion, and it stated that a function f is continuous at a point A if and only if given any sequence xn that converges to A, the sequence f of xn also converges to f of A. As this technique was extremely useful in the study of functions from R to R, we might ask whether we can use a similar technique for functions from Rn to Rm. However, there remains a question. What is the meaning of a sequence in this different context that we are now interested in? To answer this question, let us first recall what was a sequence of real numbers. Recall that a sequence of real numbers was a function from the set of natural numbers to the set of real numbers. Given such a function, we could list the real numbers s of 1, s of 2, s of 3, etc. And for simplicity, we often denoted s of 1 as x1, s of 2 as x2, s of 3 as x3, and so on. More generally, the nth element in the sequence is written as xn, which is equal to s of n. Now we can ask a question. What would be a sequence of elements in Rn? Or in other words, a sequence of vectors in Rn. A sequence of vectors in Rn would be a function from the set of natural numbers to Rn. That means the vectors s of 1, s of 2, etc. forms a sequence. Once again, we may express s of 1 as x1, s of 2 as x2, and so on. Notice that I have used superscript instead of subscript this time. That is because each of these xi's are vectors and they have coordinates. And it would be useful to denote xi as xi1, xi2, etc. up to xin. Now that we have understood what is the meaning of sequences in Rn, the next step is to understand convergence. So let's try to see how to define convergence of a sequence of elements in Rn. The basic idea was that we want the elements of the sequence to be eventually as close as we want to a fixed point A. The proximity is captured using norm and the eventuality is captured by taking large values of I. So more precisely, we say a sequence xi in Rn converges to a point A in Rn if and only if for every epsilon greater than 0, we can find a natural number n such that norm of xi minus a is less than epsilon for all I greater than n. Let us go through the intuition once more. We saw that norm acts like a distance. So when we say norm of xi minus a is less than epsilon, we mean that the distance between xi and a is less than epsilon. And by making epsilon arbitrary, we are saying that we can make xi as close to a as we want. But this will happen only eventually. That means it will happen only for large values of I. And this is the basic intuition behind the idea of convergence of sequences. We saw earlier that the continuity of a function can be expressed in terms of the continuity of its component functions. Similarly, we can express the convergence of a sequence of points in terms of the convergence of its coordinates. More precisely, a sequence xi converges to an element A in Rn if and only if the jth coordinate of xi converges to the jth coordinate of A. The proof is also quite analogous to what we had seen earlier, but as it is quite involved, there is no harm in seeing it again. The basic idea was an identity which we had proved earlier. It states that the maximum of 1 less than or equal to j less than or equal to n of mod of xij minus aj is less than or equal to norm of xi minus a is less than or equal to square root of n times maximum of 1 less than or equal to j less than or equal to n mod of xij minus aj. Now let us use the identity to prove the theorem. First, assume that xi converges to A. That is, there exists some capital N such that whenever I is greater than capital N, norm of xi minus A is less than epsilon. Which would imply that each of these terms is less than epsilon whenever I is greater than capital N. Which means xij converges to aj. So we have proved one of the two implications. Now let us prove the other implication. That is, we are going to assume that xij converges to aj. Which means you can find a capital N such that whenever I is greater than capital N, this quantity is less than or equal to epsilon by root n. Now there is some subtlety here. Actually, we will get an nj for each j such that whenever I is greater than nj, mod of xij minus aj is less than epsilon by root n. And we need to take an n that's greater than or equal to all these nj's. In other words, we are going to take n to be equal to maximum of all these nj's. If you take such an n, then mod of xij minus aj will be less than epsilon by root n for all j. And once you take that n, we know that norm of xi minus a will be less than root n into epsilon by root n, which is equal to epsilon. Thus, we see that xi converges to A. And that completes the proof of our theorem. When studying sequences in R, one of the most important properties was uniqueness of limits. So let's try to prove that this uniqueness holds even for sequences in Rn. To prove this, we will assume that xi converges to A and xi converges to B, and from this assumption we will prove that A has to be equal to B. In other words, the limit is unique. If we focus on xi converges to A, it means that for every epsilon greater than 0, there exists some natural number n1 such that norm of xi minus A is less than epsilon whenever I is greater than n1. Similarly, if we focus on xi converges to B, we see that for every epsilon greater than 0, there exists some natural number n2 such that norm of xi minus b is less than epsilon whenever I is greater than n2. So now we take n to be equal to maximum of n1 and n2. In other words, if I is greater than n, it is greater than n1 and n2. That's the idea. As xi minus x is equal to 0, I can write norm of a minus b as norm of a minus xi plus xi minus b. And by applying triangle inequality, this is less than or equal to norm of a minus xi plus norm of xi minus b. And if I is greater than n, both these quantities will be less than epsilon. Thus, the sum is less than 2 epsilon. Thus, we know that norm of a minus b is less than or equal to 2 epsilon for every epsilon. As epsilon is arbitrary, this means that norm of a minus b has to be equal to 0. Which means a is equal to b, and that proves our theorem. Let us quickly look at some examples of sequences in R2. Consider xi to be 1, 1 by I. The x coordinates form a constant sequence 1 which converges to 1. On the other hand, the y coordinates converge to 0. So the sequence converges to 1, 0. Let us see a slightly more complicated example, namely xi is equal to I by I plus 1, 2 plus 1 by I the whole square. Once again, what we studied in analysis enables us to show that I by I plus 1 converges to 1, and notice that 2 plus 1 by I the whole squared is equal to 4 plus 2 by I plus 1 by I squared. Further, 2 by I converges to 0 and 1 by I square also converges to 0. Thus, we know that 4 plus 2 by I plus 1 by I square converges to 4 plus 0 plus 0, which is equal to 4. Thus, the sequence xi converges to the element 1, 4 in R2. Similarly, you can construct more examples and I hope you will be able to do it on your own. We will now return to the motivating theorem of the video, namely the sequential criterion of continuity. It states that f from Rn to Rm is continuous at A if and only if for every sequence xi that converges to A, the sequence f of xi also converges to f of A. First, we will prove the easy side of the theorem, namely if f is continuous at A, then for every xi that converges to A, f of xi converges to f of A. As f is continuous at A, we know that for every epsilon greater than 0, there exists delta greater than 0 such that norm of x minus a is less than delta implies that norm of f of x minus f of a is less than epsilon. Now let us take a sequence xi that converges to A. As xi converges to A, we know that for every delta greater than 0, we can find some natural number n such that norm of xi minus a is less than epsilon whenever I is greater than n. But if norm of xi minus a is less than delta, then by continuity of f, we know that norm of f of xi minus f of a has to be less than epsilon. Which means that the sequence f of xi has to converge to f of a. As this xi was completely arbitrary, we have shown that for every xi that converges to a, f of xi converges to f of a. And that completes the proof of one implication. Now let us try to prove the other way, namely if for every sequence xi that converges to a, f of xi also converges to f of a, then f is continuous at a. To prove this, we will use the contrapositive. In other words, we will prove that if this is not true, then this also cannot be true. That is, if f is not continuous at A, then there exists some sequence xi such that xi converges to A, but f of xi does not converge to f of A. Let's try to prove this next. The only difficulty lies in understanding the meaning of f is not continuous at A and f of xi does not converge to f of A. And here the difficulty lies in negating sentences. The definition of continuity says that for every epsilon greater than 0, something holds. Its negation would say that there exists some epsilon greater than 0 for which that's not true. But what should hold? There exists a delta greater than 0 such that something happens. So its negation would mean there does not exist any such delta. In other words, whatever delta you take, it is not holding true. In other words, whatever delta you take, there will exist some x such that norm of x minus a is less than delta, but norm of f of x minus f of a is not less than epsilon. In other words, norm of f of x minus f of a is greater than or equal to epsilon. And in similar fashion, we can also negate the meaning of f of xi does not converge to f of a. F of xi converges to f of a means that for every epsilon greater than 0, something holds. So its negation would mean that there exists some epsilon greater than 0 for which that something does not hold. But what is the something? The something states that there exists some n such that norm of f of xi minus f of a is less than epsilon whenever I is greater than n. So its negation would mean that there does not exist such an n. In other words, whatever n you take, you cannot guarantee that norm of f of xi minus f of a is less than epsilon for all I greater than n. In other words, you can find some I greater than n such that norm of f of xi minus f of a is greater than or equal to epsilon. Now assume f is not continuous at A. That means there exists some epsilon greater than 0 such that something happens. Choose that epsilon and fix it. Now for this epsilon, whatever delta you take, something happens. So take delta to be equal to 1 by a. Now given any delta, you can find an x that depends on delta such that norm of x minus a is less than delta, but norm of f of x minus f of a is greater than or equal to epsilon. So for each delta, that means each I can find some xi such that norm of xi minus a is less than delta, but norm of f of xi minus f of a is greater than or equal to epsilon. Now these xi's form a sequence. Further, as 1 by I converges to 0, we can see that norm of xi minus a converges to 0. In other words, xi converges to a. However, as norm of f of xi minus f of a is greater than or equal to epsilon, we see that f of xi does not converge to f of a. Thus, we have produced a sequence xi such that xi converges to a, but f of xi does not converge to f of a. And that completes the proof of our theorem.